We're recording. Your voices are now on the video. Want to let you know? That doesn't mean yell louder. Yes. All right. So, listen up. All right. So here we go. The first part of this I'm going to go through fairly quickly because I'm assuming it's stuff that you've learned before. We might talk about it in a little more detail than you're used to, okay? But I don't think this is going to be too bad. We're going to talk first about the 4 states of matter. What? Did I just say 4 states of matter? Close. All right. So the 4 states of matter right here: solid, liquid, gas, and the one that's not talked about. First empty, blank. I'm not sure if that's really supposed to be a blank, actually. Yeah. Yeah, up at the top there, that's not really a blank. Okay, so the 4 states of matter: solid, liquid, gas, and plasma. Plasma is the one that well, you probably haven't talked about too much up until now. We're not really going to talk about it a lot in here either. There is plasma in the sun. There's plasma in lightning. Actually, we're going to talk about it in just a minute, so I'll wait a second here. There's plasma in televisions. There's plasma in some welders. All right, so it's based on particle arrangement. That's how we classify something as a solid, liquid, or gas. How are its particles arranged? Okay, and we're going to talk more about that later in the year when we talk about intermolecular forces. But for now, just, the basics about states of matter will be fine, okay? Based on the energy of the particles, how fast are they moving? Okay, that's what we mean when we say energy, and it's based on the distance between the particles. How spread out are they? Okay? All right, everybody have that so far? Okay. So the kinetic theory of matter basically says that matter is made up of particles which are in continual random motion. Any guess what sorts of particles we're looking at right now? Yeah, those are gas particles. They're very spread out. They're moving fairly quickly, very randomly. Okay? But the kinetic theory of matter says that all particles do this to some extent. Even the particles in this table are moving a little bit. Okay? Not much. They're just kind of vibrating back and forth. But they are moving. Okay? So solids first. And again, I'm not telling you anything you don't know. What's that? Ernst. He's really good at the PowerPoints. Yeah. So solids are tightly packed. They're vibrating in a fixed position. So they don't really slide past one another or anything. They're just kind of there. Just like you see right here. They're all packed in close together. And you can see them move just a little bit. Right? They're all just barely vibrating. But they are still moving. Okay? So solids, again, you've learned this since probably first grade. They have a definite shape and a definite volume, right? Unless you smash the shape, then you can change it. But then most of the time it will stay the way that you changed it, right? You can change any of these by adding some energy to it. Well, okay, that's true. But ice is going to melt at room temperature anyway. So you add heat to it, okay? If you add heat, then you're going to change that into a liquid. Now notice what the particles are doing. Yeah, I like these notes too. That's good. So liquid, still tightly packed, all right? So there's not much change in volume when you melt a solid into a liquid. But they're far enough apart now that they can kind of slide past one another. Okay? And they have an indefinite shape, but they have a definite volume. Again, you've known this since, I don't know when, for a long time. Okay? And then there is gases. There are gases, I suppose would be the correct way to say that. So gases, very far apart. They move freely. They're not really attracted to one another, so they're not stuck together. Okay? So gases have an indefinite shape and an indefinite volume. They will spread out. They'll take up as much space as you give them. All right, now plasma. This is the one you're probably less familiar with. So you add more heat even to a gas, eventually you'll get to a plasma. I think Ernst likes plasma. What happens if you raise the temperature to super high levels between 1,000 and 1,000,000,000 degrees Celsius? Will everything just be a gas? Okay, and the answer is, what happens is you get these things hot enough, and basically you start breaking apart the actual atoms themselves. You start stripping the electrons off of the atoms, okay, if you get them hot enough, and they become ions, okay? So plasma is basically just a gas that's had some of its electrons stripped off. It's an ionized gas. All right, so there's the electrons zipping around, and there's the positively charged particles because they... it's all moving really fast. I don't know. I would assume given the same amount of energy, the electrons are probably moving a little faster, but the movement of electrons is weird anyway. They kind of act like waves and particles at the same time. So electrons are weird. You can't even see them. When you look at them, they disappear. So, yeah, they're strange. When you don't look at them, they don't disappear. When you look at them, they disappear. Yeah. I know. It's weird. All right, so anyway, plasma is a good conductor of electricity. It's also affected by magnetic fields, so you can contain a plasma by surrounding it with magnets. Okay? This is one of the big fields of research in trying to get fusion reactors to work. Any of you familiar with fusion? Any of you watch Spider-Man 2, the old Spider-Man? Okay, yeah. So Doc Ock, he was trying to make fusion work, right? Okay. Yeah, they had to throw it in the slightly unrealistic, but you know, I mean, don't get all your science from Spider-Man 2. But the fusion part of that, where you're crashing atoms together and creating energy, like the sun, that's fusion, okay? And that's actually being attempted. Now, the problem we have right now is that it takes too much energy to get the reaction started and to get it to continue. So we're actually pumping more energy into it than it gives off, and that sort of defeats the purpose. Well, the point is, if we could get it to work right, then we wouldn't have to rely on fossil fuels anymore for our energy. We wouldn't have to burn fossil fuels. So you could have like a little fusion car, you know, you're driving it around, throw some hydrogen in there, make it all fuse. That's probably slightly unrealistic, but fusion could provide some of our power if we could get it to work. So plasmas, like gases, will have an indefinite shape and an indefinite volume. Yep.
So is that like the particle accelerator?
The Hadron Collider? Yeah, they're essentially doing fusion there.
Because they make black holes.
Yeah, no, the worry is that they were going to make black holes, but that doesn't actually... To my knowledge, no, but that I could be wrong. Yep.
Why can only like gas be used for cars and stuff? Like why can't they put other like liquids?
Why can only gasoline be used? Well, there are other things that work to power cars.
But why can't it be like any liquid?
Well, not all liquids burn, right? You need a liquid that burns. Yeah. Okay. So plasma is the common state of matter. I'm not sure what he means by that. Common state of matter. I'm going to have to get back to you on that one. I don't know what he means by that. Okay, so some places where you can find plasma. You can find it in flames. Okay. So the sun, for example, is just a big burning ball of gas, right? There's plasma in the sun. You can find it in lightning. The air around the lightning gets superheated to a plasma for just a split second until the lightning goes away. You can find it in the northern lights. Okay, that's an example of plasma you're seeing up in space. As that, it's really not all the way up in space. It's just up in the upper atmosphere as the solar radiation hits the beginnings of our atmosphere. And then the sun is an example of a star in its plasma state. All right? So there's some examples of plasma. Plasma's fun. I like plasma because we don't, talk about it as much. What? Oh, okay. All right. So each addition of what causes a change in state? Did you notice as we were going through? Each addition of heat causes a change in state. Okay? Or each addition of energy, I guess, is what he's got up here. Typically, it's heat energy. All right, so you start with a solid, you add energy, you're going to get a liquid, you add more energy, you're going to get a gas, you add enough energy, eventually you get a plasma. All right? Okay, so now we're going to talk specifically, we've gotten through, that's all we're going to do right now on states of matter. Okay, now we're going to talk about gases specifically. And that's what the rest of this unit is going to be about, is gases. Okay, so general properties of gases here. Whoops. Okay, there we go. Gases are considered fluids. They easily slide past one another, okay? Now, you might think of fluids more as like liquids, but in the scientific definition, a fluid is anything where the particles move past one another, okay? So by that definition, gases are actually better fluids than liquids are. Yeah. Oh, thank you. Remind me about that at the very end of class, and I'll collect them. Okay? Because I want to give you points for those. Well, I'll help your grade if you did it.
I didn't find one question.
That's not a big deal. Okay. So gases are highly compressible. Because they're so spread out, it's really easy to push them together. Okay? Trying to think of an example of this. It's not that hard to squeeze a balloon, right? Well, okay, it's hard to... I mean, you can squeeze the balloon, you can make it smaller to some extent. The gas usually squeezes into a different part of the balloon, okay? But a syringe, if you've got air in a syringe, you can press that down to some point, like for shots. So gases are compressible, okay? A lot of free space in a gas, all right? The gas particles are really spread out. That's why you can push them closer together, because there's a lot of empty space there. Gases can be expanded indefinitely or infinitely. That means you give them the universe and they'll just kind of keep expanding and keep moving out, okay? So gases they expand. That's what they do. They're going to fill containers. You give them enough time, eventually it will be a uniform filling of the container. Do you know what I mean by that? In other words, it's going to be perfectly spread out all throughout the mixture, okay, or all throughout the container. And gases diffuse and mix rapidly. Do you know what I mean by diffusion? Should have talked about that in biology last year, right? Okay. And now we're talking about it in terms of gases. You probably talked about it more in terms of liquids, like inside your body, is my guess. Did you talk about gas diffusion too? Okay. So gases diffuse and mix rapidly. Diffusion basically just means you've got a really concentrated area of gas. They will spread out and fill whatever container that you give them. Okay. And they create air pressure. Okay. So we actually have quite a bit of pressure pushing down on us right now from the gases in this room. It's approximately 1 atmosphere of pressure, which there was a little bit of that on your reading questions from yesterday, wasn't there? About the pressure measurements? Okay. So these gases are pushing down on us with quite a bit of pressure. And we're going to do some demos later on in this unit to show just how much pressure they are actually pushing with. It's enough to crush things if you remove the internal pressure from those things. So there's quite a bit of pressure pushing down on us right now. All right, so let's talk about pressure. The pressure is the amount of force per unit of surface area, okay? So my best example I have of this You guys ever seen, like, either on television or probably not in real life, but maybe on television, seen a person lay down on a bed of nails?
Yeah.
Or heard of that happening? Okay. There's a very specific reason that that works. Have you ever seen someone say, hey, watch this, I'm going to lay down on one nail? That's really stupid, right? Okay? Because if they lay down on one nail and all of their body weight is, you know, going against that one small area right there, that's too much pressure for the human skin to take, and it's going to go through them, okay? So that's bad. Now, if they can distribute all their weight over a bunch of different nails, now there's not so much pressure on any one given nail, and then it actually works, okay, if you're careful. You have to know how to get onto those things correctly, otherwise you will still puncture yourself. So, but that's the idea of pressure, okay? It has to do with how much force are you exerting and how much of an area are you exerting it in, okay? Force is usually measured in newtons, area is measured in meters. That's for the standard, the metric system, okay? That's how we measure pressure in the metric system. Force is in newtons, area in meters. You guys remember in 8th grade talking about newtons? Did you guys do any of that stuff? Okay. And area is measured in meters. We've talked about meters this year. So the Pascal, newtons divided by meters, that's actually called a Pascal, right? And that's the SI, or the metric unit of pressure. Okay, then atmospheric pressure. The way to measure atmospheric pressure is using a barometer. Torricelli was the one, I believe, that came up with the idea of the barometer. So one of the pressure units is called a torr, in honor of Torricelli. Okay. All right. So the way that we measure air pressure, it's really not. It's not on here, is it? Oh, column height measures pressure of atmosphere. Yeah, you don't have anything to fill in there. So the way that this works, basically, Torricelli put a tube turned upside down into, you know, like this is a petri dish or something like that, any sort of container down below, and he filled it up with mercury. Well, first he made sure all the air was taken out of it. Okay, filled it up with mercury. So there's a vacuum up here. In other words, there's no gas inside of this tube. That's what a vacuum means, really, is that it's had all of the air sucked out of it, essentially. Okay? So this is a vacuum. So there's atmospheric pressure pushing down on the liquid here. As the atmospheric pressure pushes down here, what's it going to do to this column of mercury inside the tube? It's going to push it up, right? Okay? So you can actually measure the distance that the air pressure pushes up the column of mercury, and you can measure the pressure in any given area. The more pressure there is, the higher this column is going to go. Okay? And so there is a unit of pressure called millimeters of mercury, and that's literally what it is. It's just a measurement of how high does the mercury go in a tube. Okay? And that's one way that you can measure pressure. It typically is. You can actually do inches of water also. That is a pressure measurement. I don't know why millimeters of mercury is more standard. I really don't have a good answer for that question. But you can measure it with inches of water as well. I've seen that pressure measurement. And it seems like that would be a little bit better for the environment, you know, than mercury. So standard temperature and pressure. You need to know this. 0 degrees Celsius is standard temperature. Standard pressure is 1 atmosphere. Have we talked about this already? Standard temperature and pressure? Okay. I can't remember what I've talked about in AP and what I've talked about in here. All right. So some pressure conversions for you. 1 atmosphere is equal to 760 millimeters of mercury. Okay? Now, 1 atmosphere, the reason that's the standard Can you guess where we might measure that pressure to determine typical atmospheric pressure? Well, in the atmosphere, but where on Earth? Because pressure differs based on your elevation. Do you guys know that? Well, okay, you're on the right track, but not the equator, because there could be mountains at the equator, right? Sea level. Okay, so we measure at sea level what's the pressure of the atmosphere, and we call that 1 atmosphere. All right? So 1 atmosphere is equal to 760 millimeters of mercury, also called torr after Torricelli. These are the same thing, okay? 1 atmosphere is equal to 29.92 inches of mercury, in case you just are a die-hard, I'm going to use the English system type person. You don't like millimeters. 14.7 pounds per square inch. You guys have heard of that unit of measurement before, haven't you? Where do you usually see PSI? In air compressors, in bike or car tires, right? Well, maybe you don't have that much experience with that yet. Once you start driving, you'll have to pay attention to how inflated your tires are. 101.3 kilopascals is equal to 1 atmosphere of pressure. There are a lot of different pressure units. And then, so if it's 101.3 kilopascals, that means it's 101,325 pascals, because you just multiply by 1,000, and that will tell you the number of pascals. All right? Oh, and also about 34 feet of water. So there's your water conversion there. Okay? So, up at the top here, well, I guess right underneath that set of conversions, it's all given to you as an equality here. 1 atmosphere equals 760 millimeters of mercury, which equals 760 torr, which equals 14.7 psi. So they're all equal to one another there. Okay? So once we know that, we can do some more dimensional analysis. Yeah. So we've got a problem here that's asking critical pressure of carbon dioxide is 72.7 atmospheres. Don't worry about what the critical pressure is for right now. It has to do with phase diagrams, which we'll talk about later in the year. Okay? But the critical pressure of carbon dioxide is 72.7 atmospheres. What is this value in pascals? All right, so how are we going to figure this one out? Shouldn't be too difficult, I don't think. We're going to start with 72.7 atmospheres, because that's what they give us in the problem. We're trying to convert this to pascals, right? So I'm going to put atmospheres on the bottom. I'm going to put pascals on the top. Now the good news for you guys is these are all one-step conversions. Okay? So you don't really have to worry about the two-step stuff here as long as you can do this correctly. All right? So look at your sheet here. It's got all the conversions. 1 atmosphere is equal to how many pascals? 101,325. Okay? Pay attention to the time. Okay, so then all you do is take 72.7, you multiply that by 101,325. And we got to pay attention to our sig figs here. Okay, 7, 3, 7, and then a bunch of zeros, right? Did I put that in right? It's 101,325. So you might want to do that again, because I think I'm getting 7,366,327. Unless I typed something in wrong. I don't think I did, though. Times 101,325. Yeah, that's the number I'm getting. 737,0000 pascals. Okay? So that's 7,370,000. And that's, I'm not sure if I like that so much, so I'm going to put that in scientific notation. 7.37 times 10 to the 6th pascals. Okay. Either way is fine. They're both the correct answer. All right, so that's all you basically do with those pressure conversions. Next one here. Yeah, I'm going to have to erase this now. The vapor pressure of water. Sorry. Vapor pressure of water at 50 degrees is 12.33 kilopascals. What is this value in millimeters of mercury? Okay, so this time we've got 12.33 kPa. Kilopascals goes on the bottom. We're trying to convert to millimeters of mercury. Now this is where it gets a little tricky, but you can look at this, and I've got an equality here, okay? My equality tells me that 101.3 kilopascals is equal to 760 millimeters of mercury. So now we have a number on top and bottom. And I know that's a little weird. We're not used to that with our dimensional analysis, but you can save yourself a little time by doing it that way. Does everybody get that? That this is what your sheet is telling you, that 760 millimeters of mercury is equal to 101.3 kilopascals. All right? So on this one, when you type it in, you're going to do 12.33 times 760 divided by 101.3. And this gives us a little more reasonable number here. 92 point... we're going to, just a note on sig figs here, we're going to treat these numbers as exact numbers so they don't count towards your sig figs. You just look at the first number to figure out how many sig figs to round to. Well, it's probably a good policy. So 92.51 millimeters of mercury. All right? So that's how you do those conversions. All right. In the interest of time, what I'm going to do now is hand you your homework, which is just basically more of these pressure conversions. We are going to have a quiz tomorrow. All right? This quiz will be over the pressure conversions, and it will be over maybe just a little bit on solids, liquids, and gases and plasma. So you might just take a look at the beginning of your notes there as you're studying for it and go over as many of these as you need to go over in order to feel ready to do the pressure conversions tomorrow. Okay? Also, turn in, as I'm handing these out, here, I'll stop the video first.